So, let's begin with the main theorem which we are going to prove. So, let X be a locally compact topological space which is not compact. Okay. So, then there is a compactification so then there is another topological space which we call X hat along with an inclusion I from X to X hat such that the following conditions hold. First is X hat minus I of X is just one point which we denote P0. The second is I is continuous. Third is the image of X under I is and fourth is the image of X is dense. Okay. So, let us prove the existence of such a topological space X hat. As a set, we take X hat. So, the first condition also already tells us that so we want I to be an inclusion and X hat minus the image is just one point. So, therefore, we have to take X hat is just X disjoint union one point. Okay. So, next we have to define a topology on X hat. So, define a collection tau of subsets of X hat satisfying any one of the following two conditions. So, A is if U is an open subset of X and U is open, okay, and B is if P naught belongs to U and X hat minus U. Note that X hat, since P naught is in U, X hat minus U is a subset of X, right, which is contained in X is compact in the subspace topology. From X. Yeah. So, we let tau be the collection of subsets which satisfy these conditions, yeah, and we need to check that tau. So, let us check that tau satisfies the conditions for being a topology on X hat. Okay. So, let us check the first condition. So, we need to show that the empty set and the full set X are in tau. So, the empty set satisfies A and the full set X hat satisfies B, right? So thus phi and x hat are in tau. Okay. So next, let ui be an arbitrary collection in tau, right? So we need to show that V, which is the union of these, is in tau, right? So if all the ui satisfy condition A, then clearly V, which is the union, also satisfies. So which would mean that each of the ui's is contained inside X and each of these is open, which means the arbitrary union is going to be open. So V also satisfies condition 1, condition A, right? So let's assume that one of these, so assume that, let's say ui naught does not satisfy A, so it satisfies B, yeah, for some I naught, right? So then let's look at, so consider the set. So then V contains P naught, and therefore to show that V is in this collection, we can only show that V satisfies B. So consider the set x hat minus V, yeah. So we are forced to look at the set x hat minus V. This is equal to x hat minus union I in I ui, which is equal to the intersection I in I x hat minus ui, right? So as ui naught, okay, contains P naught, this implies x hat minus ui naught is completely contained inside X, right? So thus we can write x hat minus V is equal to intersection I in I x hat minus ui intersected with X, okay, right? So if uj satisfies A, right? So then this clearly implies that uj is contained in X, and therefore x hat minus uj intersected X is simply equal to X minus uj, right? This is an easy check. And similarly, okay, so therefore we can divide this into two parts. Intersection I in I ui satisfies A x hat minus ui intersected with X, then this whole thing intersected with intersection I in I ui satisfies B x hat minus ui, right? So this is equal to, because of what we saw here, this is equal to intersection I in I ui satisfies A x minus ui intersected with I in I ui satisfies B x hat minus ui, right? So this collection is non-empty as as ui naught is here, right. Now all these are closed of x, right, and this is a compact, each of these is a compact subspace of x, right. So this implies that x hat minus v is a closed subspace of a compact subspace of x, right, which implies that x hat minus v is compact, is a compact subspace of x, right. So this implies that v satisfies b, which implies that v is in tau, right. So therefore tau satisfies the second condition for being a topology. So finally let's check that tau satisfies the third condition for being a topology. So for that, let u1, u2 up to un be finitely many elements of tau, and we need to check that v, which is the intersection of the ui's, is in tau. Okay. So first assume that, consider the case where all ui satisfy b, right. So then v contains p naught. So b was, p naught is in each of the ui's, and x minus ui is compact, right. Right. So then v contains p naught, right. So x hat minus v is equal to a finite union of x hat minus ui. Each of these is compact, right, and clearly a finite union, of compact subspaces is compact, right. So this implies that v satisfies b, which implies that v is in tau, right. So now let's consider the second case, which is so assume that one of the ui's satisfies a, right. So then v does not contain p naught, and we need to show that v satisfies a, right. That's the only way we can show that v is in tau. Yeah. So notice that as v does not contain p naught, it is already contained in x. Note that v is contained in x as p naught is not in v, right. So thus we can write v as v intersected x, which is equal to intersection I equal to 1 to n ui intersected x, right. So if uj satisfies b, right, so then it is easy to check, or I mean, so this is always true. Uj is equal to x hat minus x hat minus uj, right? So intersecting both sides, this is always true. This is a very simple synthetic statement since uj is contained in x hat. So intersecting both sides with x, so this implies that uj intersected x is equal to x minus x hat minus uj, right? But x hat minus uj is a compact subspace of X, as uj satisfies B. This implies a closed subspace of X. Right? This implies X minus x hat minus uj is an open subspace. Right? So thus we get that V is equal to intersection I equal to 1 to n ui intersected x. Yeah. So we can break this intersection into two parts. Ui satisfies A, ui intersected x, intersected ui satisfies B, ui intersected x, right? And in both cases, each of these members is open in X, right? And since a finite intersection of open sets is open, this implies V is open in X. Therefore, we have checked that tau satisfies all three conditions. Thus, tau defines a topology on X hat. Okay. Next, let us prove that so just want to see if so I should have said Hausdorff. Hausdorff. Yeah, which is what we are going to check next. So we have defined a topology on X hat. So let's check that this topology is Hausdorff, right? So let us prove that X hat is Hausdorff, right? So if x comma y are in X, so we have to take any 2 points in X hat and we have to construct neighborhoods of these points which are disjoint. So if x and y are in X, right, then we are done as X is Hausdorff. Okay. So we can, since X is Hausdorff, there are two neighborhoods, there are two open subsets U and V inside X, such that U contains X and V contains Y, and their intersection is empty. And since both these U and V are in tau by condition 1, yeah, so therefore in this case we are done, right? So let's consider the next case. If X belongs to X and Y is equal to P naught, yeah. This is the only other case we need to consider, yeah. So then let W be an open subset of small x in X such that the closure of W in X is compact, right. Such a W exists because we are assuming that X is locally compact, right. So then X hat minus W closure satisfies condition B, right, and is an and so is an open subset of X hat, right. So clearly W and X hat minus W closure are disjoint. So it's an open subset of X hat containing P naught, right. So thus we have found an open neighborhood of X hat, an open subset of X hat containing P naught, another open subset of X hat which contains W such that their intersection is empty. Yeah. So this shows that X hat is Hausdorff. Okay. So next let us prove that X hat is compact, right. So suppose we are given an open cover. So X hat is equal to union UIs, right. So there is a UI naught such that P naught belongs to this UI naught. Okay. So thus X hat minus UI naught is contained in X and is compact. Okay. So now so X hat minus UI naught, this is contained in this union UI, and this implies that X hat minus UI naught intersected X is contained in this I in I, UI intersected X, right. So now exactly as we saw over here, right, if UI satisfies B, then UI intersected X is an open subspace of X, right. We saw this above, right. So this is, if UI satisfies A, then obviously UI intersected X is equal to UI and it's an open subset of X. And on the other hand, if UI satisfies B, then as we saw above, UI intersected X is an open subset of X, right. So but this is equal to X hat minus UI naught, since X hat minus UI naught is contained in X. Yeah. So therefore this open cover, since X hat minus UI naught is compact and it's a subspace of X, and we have found an open cover of this inside X. So this open cover has a finite subcover, right. So thus X hat minus UI naught is contained in finitely many Uij. This implies X hat is contained in Uij union UI naught, right. So this proves that X hat is compact. Okay. Next, we have the obvious inclusion, denote the obvious inclusion. Right. So if U contained in X hat is open and U is of type A, U satisfies A, then clearly I inverse of U is simply equal to U, which is open. Yeah. On the other hand, if U satisfies B, then as we saw above, U intersection X, yeah, not Xj, is open in X. Yeah. So this implies the I inverse U, which is exactly U intersection X, is open. Thus in both cases the inverse image of an open subset is open, so this implies I is continuous. Right. As we already seen that X hat is Hausdorff, right, and in a Hausdorff topological space a single point is always closed, is a closed subset, because the complement is an open subset. Yeah. So this implies that I of X, which is equal to X hat minus this closed subset, is an open subset. Right. And the last thing we need to show, that finally we need to show that I of X is dense in X hat. Right. So for this, let U be an open set in X hat which contains P naught. Right. So we need to show that U intersection X is non-empty. Yeah. So if U intersection X is empty, right, so this will imply that P naught, so as this will imply, yeah, as X is equal to X hat is equal to X disjoint union P naught, this will imply that U is equal to P naught. Right. That is, the singleton set P naught is open in X hat. Right. So thus this will imply that X, which is equal to X hat minus this open subset contained in X hat, is a closed subspace, which will imply that X is compact. Right. So but this contradicts our assumption. Right. So thus U intersection X is not empty, which implies that I of X is dense in X hat. So this completes the proof of the theorem. So we will end this lecture here.